Hello everyone, my name is Dr. Purbe, and this is my lab 4 where I'll be analyzing the motion of a falling slinky. The purpose of this lab is to analyze the motion of a falling slinky. In this lab, we'll use Tracker to track the motion of a falling slinky, and after collecting the observed data, we'll build a computational model using VPython on GlowScript. An overview of the data suggests that the predicted and the observed motions were quite similar, and the bottom of the slinky fell after the top reached the bottom. In other words, the slinky collapsed before it fell down to the bottom. The fundamental principles in this lab are as follows. The momentum principle, which states that the net force can be quantified as a rate of change of momentum, where F net is equal to delta momentum over delta time, delta t. The velocity update formula, which states that the final velocity is equal to the initial velocity plus F net over m times delta t, and the position update formula, which states that the final position is equivalent to the initial position plus the average velocity times delta t. In this experiment, we'll be considering three forces: drag force, the weight force, and the tension force. The tension force is a contact force that is transmitted through the slinky throughout the length of the slinky. The gravitational force is the force of gravity, which can be quantified as negative mg. And the drag force, which is a dissipative force that is proportional to the object's velocity, which can be quantified as negative bv squared, where negative b is just a coefficient of drag. In this experiment, we'll consider the Earth and the slinky as the system. The forces acting on the system include the tension, the drag, and the gravitational force. The mass of the slinky is calculated to be 0.218 kilograms, and the initial position of the slinky is 0.0039 meters above the ground. Here is the overview of the results. In the time it takes from the top of the slinky to get to the bottom of the slinky, which is roughly 6.2 seconds, the bottom of the slinky stays stationary. However, after the slinky collapses, the bottom of the slinky falls along with the entire slinky. Here is the computational model we built. This code initializes the ball, which is used to represent the slinky, and it defines the initial conditions of this experiment. Here we set the mass of the ball to the slinky to be 0.218, the initial position to be 0.03939 meters, and the initial velocity to be 0. T is set to be 0 and delta t is 0.033, which is the frames per second. G is 9.8 and the coefficient of drag is set to be 37. In our first calculation loop, we calculate the time before the top reaches the bottom. Until the time reaches 6.2 seconds, we define weight to be mg, negative mg, the tension force to be mg in the opposite direction, and the net force to be the sum of the two forces. We use the position update formula and the velocity update formula to append the position, and we plot it to calculate the changes in position on the y position of the ball. After the top collapses and it is time for the slinky to begin falling, we calculate the weight to be negative mg, and we consider drag, where drag is negative b times the magnitude of the velocity squared times the velocity direction, the normalized velocity. Net force here is the sum of the weight and the drag force. Again, we use the velocity update and the position update formula to keep track of the ball's position. And we plot the position to track the position of the slinky. Here is the graph we get from the predicted motion. As you can see, it looks quite similar to the observed motion. And when plotting them side by side, we see that the observed motion and the predicted motions are quite similar. We can see a little deviation near the end. However, overall, the model was a great fit for the observed motions. And the possible sources of error that led to this deviation could be the incorrect tracking of the motion in the slinky in Tracker, and incorrectly calibrating the axes and the length in Tracker. When considering the bottom, yes, the bottom of the slinky stays stationary until the slinky collapses. When the top is first released, the bottom of the slinky experiences equal and opposite forces in the form of tension and weight. Here's the free body diagram where tension faces up and gravity points down. A net force of 0 causes the bottom to remain stationary. However, when the slinky collapses, there is a net force downward, causing the slinky to fall. As the bottom is falling, it is met with drag that counteracts the gravitational force. Thank you.